the primary goal of this video is to prove the finite geometric series formula that we have right here, because we will be using it to find the sum of the present values of the annuity and also for future values and more going forward. But as well, because this is very abstract, I want to show you an example so we can kind of read between the lines and cut to the chase about what's going on here. But I wanted to show you the idea of it in this video. Basically prove geometric series sum. Yeah, so let's move to the whiteboard for a little bit and try to work on this. So basically what I've written here is, if you're wondering like what is the beginning, but what I have is written the generic nth partial sum of a geometric series. So remember, generic formula for geometric series, AR to the n minus 1. You start with term A, and you're going to multiply successively by r's, starting with the first term, moving all the way to the nth term. So if we are to expand that, we're going to start by plugging in 1. That would give us AR to the 0, which is just A, the first term. If we plug in 2, we're going to get AR to the 1, this. But basically, the expansion of the geometric series, we've got the first term. Then the first term times the common ratio. Then we're multiplying by another r, multiplying by r, multiplying by r. And what we get is a series of, say, for example, 2, 4, 8, 16, 32, 64, etc. And it's going to stop at some generic point, n for the arbitrary point. And basically, this could be any geometric series with any first term, any common ratio, and any last term. So my point is, there is a simple way to find the sum of this series. It's like, but it's kind of cool. It's kind of weird. Let's see how we do it. So it's done by an observation that if we're examining this long series, notice there's a lot of commonality in that it sort of looks like polynomials. We got r squared, r cubed. But if we were to take the geometric series, the whole thing, and multiply through by another r, and this is something you would probably not think to do if you weren't already aware of how this proof is done. But if we multiply through by r, all of this will also need to be multiplied through by r as well, which would leave us with AR plus AR squared plus AR cubed plus AR to the fourth, dot, dot, dot. And then the final term in that series, ARn minus 1, will be multiplied by a singular r. And if I multiply that by an r, since that is one r, it will be, the exponents will add, which will give us n minus 1 plus 1, which is just n. So that would leave us with AR to the n. Or a more simple way of looking at this is, when we multiply by r, all of the degrees of the r's increase by 1. It goes from 0, 1, 2, 3, etc. to 1, 2, 3, 4, n. And so n minus 1 increased by 1, because that's what they all did. And so, well, cool, what's the point, Professor Havens, is notice that if I'm comparing these two series, a lot of these things are the same. Like, literally, both of them have AR squared, AR cubed, R. I'm going to start to sound like a pirate if I say R too many more times. That was a really terrible joke. Wow. Anyways, but if we actually take the difference of these two things, if I take the nth partial sum, and this is something we don't know. What's the sum of it? What happens if I add up 1 plus 2 plus 4 plus, that's kind of what we're trying to figure out. But if I were to take Sn and subtract Rsn, we see that a lot of that stuff overlaps and would cross cancel, because AR minus AR will cancel AR squared minus AR squared, and et cetera, et cetera, et cetera. And since that series is a complete geometric series, every term will be in there by assumption. Every one of those will cancel. AR to the fourth would be the next one. AR to the fifth would be the next one, which would cancel with AR to the fifth. But basically, if I think about, even AR to the n minus 1 would cancel with the one right before AR to the n, because basically we don't know how many terms are in here. So it could be 20 payments, it could be 50 payments, but basically all of those would overlap, because this one had one additional term and this one had one additional term at the end in the difference. So what that would leave me with is a minus AR to the n, and this would give us the difference between the nth partial sum, basically the sum of all the payments minus the ratio times all the payments. And with a little bit of algebra, I could factor out the nth partial sum from the right-hand side here. And the reason I would want to do this, I could also factor out a from the right-hand side if I so chose, is because my goal here is to figure out what is Sn. What is the formula for the generic sum of that series? And now I could divide both sides by 1 minus r to finish isolating that, which would leave me with the nth partial sum formula, which is a times 1 minus r to the n over 1 minus r. And that is the generic formula for the sum of a geometric series. And anyways, that is what I had in the slide there, that formula, which is a little bit mysterious. But in summation, every geometric series, assuming it's finite, has a sum, a predictable sum given by this formula. And in the next video, I will do an example just to help with some specifics and hopefully to make a little bit more sense.